Hello. In this video, we will go over using StatCrunch to find probabilities for binomial distributions. Okay, so we want to start off. We need to have StatCrunch. That's the tool we're going to use. So you want to open StatCrunch. Once you've opened StatCrunch, you want to select Stat, then Calculators, and then Binomial. And if you do that, that will load the binomial calculator window that is presented here. Okay, so what we're going to be doing is we're going to be going through and just entering values in here at the bottom. And by entering values, we can go through and come up with probabilities. All right, let's just look at an example. So if we want to find the probability of getting 4 heads on 10 coin flips. To go through and find a binomial probability, we need 3 things. We need the number of trials, we need the number of successes, and we need the probability of each success. So if we're doing 10 coin flips, then the number of trials is 10. If we're doing coin flips, then the probability for success is 0.5. And if we want to get 4 heads, then we're going to enter X, 4 for X, which is the number of successes. Okay, so when you're, we'll show this, I'll show the screen on the next screen, but if we want to go through and find the probability of getting exactly 4 heads, then you want to have an equal sign. Okay, that's for the inequality. Not an equal sign actually is not an inequality, but you know what I mean. You want to enter an equal sign on the calculator. All right, if you go ahead and hit compute, what should happen is that the bar at x equals 4 should be in a different color, and the probability, which is around 21%, should appear after the equal sign. All right, so this is what it should look like. Okay, so we've got the number of trials, which is 10, 50%, flipping coins. We want to get 4 heads, put an equal sign where the inequality was, and then you should see this. And you can kind of barely make out, maybe depending upon how large a screen you're looking at, but the bar at 4, right? So what we have here, this is the binomial distribution, the entire thing, right? So you've got a visual of the entire binomial distribution, and what we've done is we've gone through and just highlighted the outcome that was modeled in the problem, which is that we got exactly 4 heads. And so if you look at the height of that and estimate it, it's around 20%. And so that's the result. So let's look at another one here. So let's say we want to find the probability of getting at least 4 heads on 10 coin flips. All right, so we're still doing 10 coin flips. So you want to leave 10 alone, leave n alone and leave it at 10. We're still doing coin flips. It's still 50% for success. And 4 is still the important number when it comes to successes. However, this time we're doing at least, which is not the same thing as doing exact, right? So we want at least 4 heads. So if you had 4 heads, 4 heads does meet the at least requirement, right? 5 heads also does, 6 heads does, 7 heads, and so on. So what you want to do is you want to change the inequality to be greater than or equal to. That is what at least means, and then press compute. If you do that, then what you should see is all of the bars at x equals 4 and above should be in that different color. And we should get roughly an 83% chance. So there's an 83% chance that if you flip a coin 10 times, that you're going to get 4 heads. And we can see here, if you look closely, all the bars that are to the right, which is, at least, are all red. And so that's what's modeled here by the situation described below. All right, what's the probability of getting more than 4 heads? More than 4. Okay, so number of trials doesn't change, probability doesn't change. 4 is still the important number here. However, more than is just greater than. All right, so at least is greater than or equal to. More than, it does not include. Right, so if someone said, is 4 more than 4? No, 4 is not more than 4. So 4 is equal to 4. 5 is more than 4, though. So what you want to do is you want to go through and change the inequality to a greater than symbol to go through and model what more than means. And if you go ahead and hit compute, what you should see is the bars at x equals 5 and above should be in the different color this time, and we should get 62%. All right, so the probability of getting more than 4 heads, or the probability of getting 5, 6, 7, 8, 9, and 10 heads is 62%. According to the calculator. And we can see 5 and above are shaded, and that models the situation with just the greater than 4. Let's look at another example. So suppose we have the website bicyclelaw.com. Only 5% of stolen bicycles are returned to the owners. Oops, there's a little typo there. Missed the L. Find the probability that exactly 10 bicycles will be returned if 235 are stolen. All right, so that's our experiment, and we just want to figure out what do we fill in. All right, so the number of trials, if we're trying to figure out 235 are stolen, how many are returned? What's the probability that 10 are returned? So 235 is the number of trials. There's a 5% chance that on any given trial, the bicycle will be returned. And then 10 is going to be the number that we're trying to find probability of. So that's the number of successes. And this is exactly 10, right? So not more than 10, not less than 10, exactly 10. So you want to put an equal sign where the inequality is, and then press compute. If you do that, you should see the bar at x equals 10 is shaded in a different color, and 11% appears after the equal sign, and that's our probability. And so you can see this, it could, again, difficult to make out, but the bar at 10 is red, and the others are like dark gray. And we've got the 11%. That is the probability. So if 235 bikes are stolen, and the probability that any given bike is returned is 5%, then the probability that exactly 10 of those bikes would be returned is 11%. The 3-year recidivism rate of parolees in Texas is about 20%. In other words, what does that mean? It means that 20% of released prisoners will return to prison within 3 years of their release. Suppose a prison in Texas releases 15 prisoners. What's the probability that exactly 6 of the 15 will end up back in prison? All right, so how many are being released? 15, that is the number of trials. There is a 20% chance that the individuals do end up back in prison. And we want to know the probability that 6 of those do end up back in prison. So 6 is going to be X for the number of successes. And then we want it exact. So we're not asking to find more than 6 or less than 6 or at least 6. It's exactly 6. So you want to change the inequality to an equal sign and then press compute. If you do that, the bar at x equals 6, that's the lone success here, should be in that red color. And there is roughly a 4.3% chance that that would happen, that 6 of the 15 will return to prison. All right, so that's the 6. You can see it's kind of in red, and all the information is entered in here. 15 trials, 20% chance, and exactly 6 return to prison. All right, let's look at another example. So for a test of psychic abilities, researchers have asked the sender to draw 10 cards at random from a large deck of Zener cards. Recall that the deck contains equal numbers of 5 unique shapes. The receiver guesses which card the sender has drawn. Okay, so you got somebody, they're drawing 10 cards. They're trying to send to the other person what the card is, and then the other person is making guesses. What's the probability of getting exactly 5 correct answers if the receiver is simply guessing and has no psychic ability? All right, what's the probability that the receiver will get 5 or more of the cards correct? Again, assuming no psychic ability. What's the probability of getting fewer than 5 correct? All right, so what we want to do is the number of trials, that's the number of cards that are being, what are we doing with them? They're being drawn at random. There we go. The number of cards that are being drawn at random is 10. Since there's 5 cards and you're guessing at random, there's a 20% chance that you're going to be correct on each guess. And then we want to know, all of these are relative to 5, right? So 5 exactly, 5 or more, fewer than 5. So we want to enter 5 for X. And then we'll go through each of the different cases that answers each of those problems on the following pages. Which ones are which? All right, so the first one is exactly. So for that one, we want to put equals where the inequality is. The probability that we'll get 5 or more. All right, that's at least. The same thing as at least. And so we're going to have, that's going to be greater than or equal to. And then the probability of getting fewer than, so fewer than is like the same thing as more than, it's you use less than. So there's no equal to there, right? So 5 is not fewer than 5. So 4 is fewer than 5. And so we've got equals, greater than or equals, and less than. Let's take a look. All right, so we've got equals, and that's about a 2.6% chance, 2.6% chance that you could go through and guess 5 cards out of 10 completely by luck, completely by random guess. All right, then this part B, greater than or equal to, there is a 3.3% chance roughly that you would get at least 5, that you'd get 5 or more. Okay, so you get 5 or 6 or 7. If you add up all those, then that's your probability of getting that number of cards correct just by randomly guessing. And then the fewer than is going to be 5 or is going to be less than 5. Sorry, so it's going to be you get none, 1, 2, 3, or 4, and that's quite a high probability that you're going to get fewer than 5. That's 96.7%. Okay, and then last but not least for this one, we picked a homework example. In a certain area, 30% of people own a cat. Find the probability that exactly 2 out of 6 randomly selected people in that area would own a cat. And then in a random sample of 6 people, find the probability that more than 3 own a cat. All right, so the probability that exactly 2 out of the 6 would own a cat. So the number of trials there is 6. The probability is 30%. And the number of successes is exactly 2. So we want the inequality, we want to replace that with an equal sign, and then go ahead and hit compute. And if you do that, there is a 32% chance, according to the calculator, and the image is on the next slide. We go through and repeat the experiment by picking 6 more people. And we want to find the probability that more than 3 own a cat. So more than 3. So we've got number of trials is still 6, probability is still 0.3. And the important number there is the number of successes is 3, but the inequality needs to be just greater than, right? More than does not include equal to, so you just want to have greater than. And if you do that, the result is going to be about 7%. Okay, so let's look at those. So here we've got the equal to, that produces the 32%, and you can see the 1 bar there is shaded that represents the successes. And then greater than 3 would be, it's kind of hard to tell, but you can see that the 4 and 5 and 6, those are shaded, and there's only a 7% chance that if you randomly selected 6 people in this area, that you would get 4, 5, or 6 own a cat. All right, and that is the video on how to go through and use StatCrunch to find probabilities for binomial distributions. Thank you for watching, and I'll see you next time.